it. So, this is the real x and imaginary x. So, my pole is shifted up, right, x equal to I epsilon, epsilon is positive. Okay. So, pole is shifted up. Now, nobody can object, okay. I can do the integral along a line, because I am not the pole is singularity is not on the real line, on not on that x axis. Now, we take epsilon going to 0 limit. So, this is what we will do. So, this Cauchy's prescription. Okay. So, this is what I have drawn it here. So, basically well, this origin is still a problem. So, when epsilon goes to tries to hit the origin, we change our contour. So, I go like that, that is what I am going to do. Okay. So, I am going to define few more things, so just hold. Okay. So, this is what I am going to do the integral. So, we redefine our integral, well, not redefine, we rewrite our integral in the following manner. So, the first one goes from a to minus infinity, a is somewhere here. Okay. So, a to minus delta. So, this is the first part, this one a, okay, a is here. Then minus delta to delta is this integral. I am avoiding that origin, okay. Though I have shifted the pole, but basically pole can go very close to the origin. So, it just go below. So, this is b and the c is delta to b, okay, this is c. Okay. So, we rewrite like that. Now, we will again do bit of juggling around. So, a to minus delta and delta to b, a and c together we put it here and let delta go to 0. So, my delta is going very close to the 0 origin. Okay. So, this integral is now defined. Okay. I am avoiding the singularity, okay, and this is called principal value in fact. Okay. And this part I am going to do it, I am going to compute this part by complex integration. Okay. So, right now I generalize x to a complex variable and I am going to do this second part using complex integration. So, the a plus c is called principal value p. Okay. P stands for principal value, okay, this principal value, and which is I am going to show in the next slide that it is a meaningful number. It is a limit, of course, I am avoiding the singularity, but I go, my delta is tending to 0, okay, and this part I am going to compute separately. Is that clear? So, that is the definition of principal value. Principal value avoids the singularity from both left and right. Of course, you may say, what is the guarantee that principal value is a finite number? Is it converging or not? Okay. So, there is a simple argument which is a nice argument again by Cauchy. So, look this let us get this picture. Now, I can expand this fx around origin, singularity is at x equal to 0. So, expand fx around origin. So, it is f0 plus x f prime 0, okay, we need only to first order. Now, f0 by x, okay. So, we basically get f0 by x plus f prime 0, okay, f0 by x dx plus f prime 0 dx. Now, problem is near the origin. Now, near the origin, if you can see that f0 is a number, right, I mean f0 is a finite number, we assume that f0 is convergent, f0 has no singularity or fx has no singularity, okay. So, f0 by x is an odd function in x, right, f0 is a constant. So, this integral around minus delta to delta, this one in this singularity regime, they almost cancel each other. You understand, no? The dx by x. So, this in fact this part you expect some problem, right, is a singularity, but I know that this part is basically going to cancel each other from left and right. So, this principal value when you take the limit delta going to 0 is going to give us a meaningful number, is convergent. So, cancel at both sides for small delta and my answer is finite. Okay. And in fact, we will see that we will find this integral very often in field theory. Okay. So, singularity is not a problem and we can get a finite number. Of course, in field theory we want to get a finite number for mass, charge, coupling constant. So, we need that this prescription. Is that clear? The definition of principal value. Okay. Now, still we need to do the other integral, one which is going from the bottom, right, I mean the complex integration. So, this is what I had in my previous slide, this one minus delta to delta. So, I have to take two limit, delta going to 0 and epsilon going to 0. So, from the top epsilon was sitting here and my contour was this one, this was my contour, no, this one. I think I have this picture here, no I do not have the picture. Okay. So, let us do this integral. The answer is I pi times f 0. Okay. How do I get this? So, it is quite straightforward. So, I am going to draw this again probably. So, this origin, this is my epsilon and this is minus delta and this is plus delta. I put a semicircle at the bottom. Now, x is a complex number now. So, we write x as r or epsilon no delta e to the power I theta, right. Delta is the radius and theta is varying from what to what, this is 0 and this is pi. Okay. Or so, I am going from, well basically I am going from the bottom pi to 0, right. So, let us write this. So, f x I expand it as f 0 plus f prime next term, but other part will be going to 0. So, f x we write as f 0 plus x f prime 0, we divide by x. So, this part when I take dx, the second term is 0, right, because delta going to 0, f prime is 0 is finite. So, all other terms will be 0 except the singularity. So, f 0 by x is a problem term, correct. So, this is what I have written, f 0 divided by x minus I epsilon dx. Now, I am taking epsilon go to 0 limit. So, we write this part, so let me write it nicely here, minus delta delta dx will be delta e to the power I theta, but theta is a variable now, right. So, I d theta, fine, and x minus I epsilon is going to 0. So, this is approximately delta e to the power I theta, this epsilon is going to 0. So, it is just x. So, let us substitute it here, delta e to the power I theta and above is delta e to the power I theta I d theta. Okay. I have to do at the circle, semicircle. So, these guys cancel and I get I d theta. Now, semicircle I go from pi to 0. Now, will it be positive or negative? It is a counterclockwise, so positive, and d theta goes from pi to 0 or well minus pi to 0 you may call it. Okay. So, minus pi to 0. So, this is I times pi. Okay. This is how a standard Cauchy integral, that is what we do, no, I mean you might recall this. So, if often we do it for the closed contour, but here we need to do only semi contour and f 0 is sitting outside, right, this f 0. So, my integral, this integral for that function, this one is I pi times f 0. Okay. So, my integral, this integral from a to b including the singularity is written as principal value plus this part, okay, I pi delta. So, this coming from singularity, okay, this is the contribution from singularity. In fact, now you can basically memorize this, that if I see integral of this sort, then I just have to write principal value plus I pi f 0. Is that okay? Now of course, we can make the change, sometimes instead of minus we get a plus here. My singularity is not above but below, right, because x plus I epsilon singularity will be below, and then derivation is exactly same, you have to close from the top, right, for this particular case. So you can derive it in a very similar manner, and you can derive other formulas. Okay. So shorthand, instead of writing the dx we can just write shorthand this one, x I mean I am just avoiding the integral. Okay. So you write 1 divided by x minus epsilon is principal value of 1 by x plus I pi delta x. This is with a plus sign, you will find that I have to do the integral at the top, and if it is going clockwise, so that is why you get a minus sign. Okay. You can easily convince yourself. I can't get into details of this, but please go through it when you are, I mean you just spend some time on it. Now instead of x I can have x minus y. So here my singularity is at x equal to 0, right, but I can have singularity at x equal to y, or rather, right. Okay. So this is the case, then this is just straightforward, this formula. Okay. So we will encounter this kind of thing very often. Okay. Now let us do an example. Now I have to compute this integral, okay, x plus I epsilon, and there is 1 plus x power 4. Okay. Now singularity is at x equal to minus I epsilon, right. Now so this is f of x. Okay. So what is the answer? Okay. So let us look at the principal value. So I just use this formula, right, principal value of this 1 by x 1 plus x 4 dx minus I pi into f 0, and what is f 0? This is f 0, this is f x, and put x equal to 0. So answer is 1. So this part is straightforward, is minus I pi. Okay. Now what is this value? Can somebody make a guess? Well, not a guess, it is straightforward. Okay, this is 0, right, because this is the odd function. No, this is even function and x is the odd function. So this integral will cancel from both left and right. In fact, we do not need to compute it, this is 0. So this integral is minus I pi. Okay. So you see, I mean you can use this formula and get the answer quite easily. Okay. The second problem is slightly more complicated, and this is often done in regular mathematical physics course, sin k by k dk, and we will find it right now in the today's class only. I will show you that you will encounter this in Green's function computation, okay, all the time. So we want to compute this. Okay. So what will I do? Let us write sin k as e to the power I k minus e to the power minus I k. You will get these PPTs, so no need to really write down all the steps. I will share this PPT, but just focus on the idea. So by the way, this integral is 0 to infinity. Now I would like to do minus infinity to plus infinity, that is what my objective is. Okay. Now you can see from this line I can make a change of, well, this is minus I k, right. So this part I can make a change of variable minus k to k prime. Okay. So this becomes exponential I k prime, okay, right, and this k will become minus, okay, and this minus minus will get absorbed. So I can this part, this with the minus exponential minus I k part is nothing but we will extend this integral from minus infinity to plus infinity, that is a negative part, alright. It is just in fact straightforward from here, make a change of variable to minus k equal to k prime for the second part, and you will get this. So, I got minus infinity to infinity 2 pi dk by 2 I k exponential I k. Great. So, it is now it is of the form of Cauchy principal value form right, because exponential I k pi k. So, now I can use the trick. So, I am now going to do this integral in a with using contour integral. Okay. So, this is okay. Now, my answer is basically at k equal to 0, sin k by k is finite number, in fact is 1 right, sin 0 by 0 is 1 limiting. So, I am avoiding k equal to 0. So, when I say that give me this answer, I am not including k is equal to 0, because that is a singularity. So, in fact, my objective is to get the principal value, avoid x equal to 0, but it turns out you can take a limit. So, this is basically the function goes like that, no? I mean oscillating function, sin x by x is that function, right, I mean it goes to 0 for large x. Now, I am avoiding this x equal to 0, but this part when delta goes to 0 is basically 0. So, that is why we write 0 to infinity, but we have in our mind that I am taking limit my lower limit to going to 0, not equal to 0. Okay, now I need to compute the principal, this one. Okay. Now there is a trick by contour integration. So, I am going to compute my integral like this. Okay. My objective is to do this integral, this plus this, right, that is the principal value. Okay. Now, I am going to make a closed contour. Okay, this red line plus this one plus the on the top. Now, I did in the last class my Jordan lemma, that this integral, because I had to close from the top, and this integral will be 0. The semicircle large one is 0. So, my closed contour, the closed contour, this the 4 parts 1, 2, 3, 4 parts. It turns out that the large circle is 0. So, but overall it should be, the whole integral should be 0, right, because singularity is only at k equal to 0, rest all the place it is analytical. So, as long as I have closed contour avoiding the pole, then my integral must be 0. So, this integral is 0. Now, as I said, this integral has 4 parts, 2 of them are the principal value, red this one is basically principal value, not basically, it is the principal value. Now, we have this semicircle, small semicircle, this part, and the large semicircle. Okay, the dk is missing here at that corner. Okay. Now, this I said is 0. Okay. So, now the whole integral is 0, that means the principal value must be nothing but negative of this, correct. So, that is what we want, and this integral, well, I am going for the top. So, I do exactly what I did before in the last slide, use k equal to e to the power delta e to the power I theta and do it. This integral is minus pi by 2, this one. Why minus? Because I am going clockwise, this is clockwise. Okay, at k equal to 0, the exponential I k is 1 and this 2 is coming here, and it is just straightforward, okay, is minus pi by 2. So, that gives me the answer, this principal value is pi by 2, because this plus this plus this equal to 0. So, this is pi by 2. Okay. So, that means this guy must be pi by 2. There is a 2 principal. Okay. This should be pi by 2, right, sin k. Okay, no. So, 0 to infinity is pi by 2, but now I put minus infinity. So, instead of 0, if I put minus infinity, then it will be pi double, no, I mean, this integral is even in x or even in k. So, if I go from minus infinity to plus infinity, which is this one, then I get pi, double of this, right. Okay. So, you will again see this integral, in fact, you find it in optics and condensed matter physics all the time. Okay. So, this is what I mean, you can, these are derivation, well, basically a byproduct of this derivation. Okay. So, I will share this, but you can easily derive this part. Okay. So, complex analysis provide important tools for solving integrals, right. It is easy. If you do it by other means, it normally it takes more time, and that is it. So, this is a pattern. I mean, because since it is being recorded in between, or if you are not understand anything, but you can ask me now. Clear to everyone? Was it done in math methods? This integral, right? Should be. Okay. So, I will close this one.